You might not know it, but there's this one incredibly elegant algorithm that is, and I mean this literally, running our world from behind the scenes. It's a secret sauce that keeps drones perfectly stable, that keeps your car's speed locked in on the highway, and that allows industrial robots to move with such precision. And here's the crazy part. Most people have never even heard of it. So today, we're going to pull back the curtain on the PID controller. Now, to really get why this thing is so ingenious, let's start with a problem that I think we can all relate to. Have you ever tried to balance, say, a broomstick on the palm of your hand? You know that feeling, right? You're constantly overcorrecting. The second you think you've got it, whoops, it's already falling the other way. Why is that so ridiculously difficult? Well, it turns out this isn't just some party trick. It's a really fundamental problem in control engineering. An electronics hobbyist named Burkei actually ran into this exact same issue. He built this awesome little seesaw that balanced itself with two propellers. He figured, he could program it with some simple if-then logic. But as he put it, trying to do it with trial and error, well, it just led to failure every single time. And the culprit here is a little thing called momentum. So let's say one side of that seesaw starts to dip down. You tell the motor, hey, power up and get us back to level. But here's the catch. By the time it gets back to level, it has picked up speed. It doesn't just magically stop at that perfect center point. No, it blows right past it. It overshoots because of that momentum it built up. Simple commands just can't keep up with the physics. And this right here is the classic balancing act problem. It perfectly shows the limits of simple reactive control. To really solve it, you can't just react to where things are right now. You've got to be a lot smarter. So, how do you solve it? Burkei realized what he needed was a true control algorithm, one that doesn't just react to the present, but one that actually learns from the past so it can anticipate the future. And that smarter solution, the one that Burkei and countless engineers before him landed on, is called the PID controller. At its heart, a PID controller is all about something called a feedback loop. It's actually a really simple idea. The system has a goal, right? We call that the set point. In our seesaw example, that's being perfectly level. Then it's constantly measuring its actual position, the output. It compares the two, and that difference between where it wants to be and where it is, that's the error. The controller's entire job is to look at that error and figure out the exact right move to make it disappear. So what is a PID controller, officially? Well, it's a control loop that is continuously calculating that error value we just talked about. And then it applies a correction that's based on three separate, distinct calculations or terms. These are the proportional, the integral, and the derivative. P, I, and D. Okay, so let's break down what those three letters actually do. Because this right here is where the real genius of this whole thing is. Probably the best way to think about P, I, and D is to imagine them as controlling the present, the past, and the future. The proportional term, the P, is all about the present. It asks one simple question: how far off am I right now? The bigger that error, the harder it pushes back. Then you've got the integral term, the I. It's looking at the past. It asks how much error has been building up over time. This is the key to getting rid of those small, annoying errors that just won't go away. And finally, the derivative term, D, tries to predict the future. It asks, how fast is the error changing? This is what allows it to sort of pump the brakes as it gets close to the target to stop it from overshooting. And the real magic is how they all work together as a team. P is like the main muscle, right? It provides the big primary corrective force. I is like the perfectionist, coming in to clean up and get rid of that tiny little bit of error that P might have left behind. And D is the shock absorber. It smooths everything out, dampens the response, and stops the system from shaking and oscillating all over the place. But here's the thing. Just having these three parts doesn't guarantee success. In fact, if you get the balance between them wrong, the system can actually become more unstable than when you started. The real magic isn't just in having a P, an I, and a D. It's in tuning them so they work together in perfect harmony. And that brings us to a process that is really both a science and an art. It's called tuning. And this right here shows you exactly what's at stake. Look at the difference. A poorly tuned system, maybe one with way too much P and not enough D, it just oscillates like crazy, spiraling out of control. But a well-tuned system, it finds its target quickly, smoothly, with almost no fuss at all. Getting from that chaotic mess to that smooth line, that is the entire goal of tuning.
So this tuning process, it involves adjusting three corresponding values called gains. We call them KP, KI, and KD. You can just think of them as three knobs. KP is the knob that controls how strong the proportional part is, KI for the integral, and KD for the derivative. The whole game is finding the absolute perfect setting for each one of those knobs.
So how do engineers do this in the real world? Well, this graph shows a really common method. What an engineer will do is intentionally push the system a little bit just to get it to start oscillating. Then they'll carefully, slowly adjust one of the gain values until those oscillations become perfectly stable and constant. Once they find that sweet spot, they can use some established formulas to figure out the ideal settings for all three gains. It's this methodical, scientific search for that perfect, stable balance.
Okay, so we've seen how it works, but let's zoom all the way out. Why is this one algorithm so unbelievably important?
It really all comes down to the power of three. Just three simple parameters, P, I, and D. When you balance them just right, they become the secret sauce behind almost all precise, automated control in our modern world. I mean, just think about it for a second. That drone you see hovering totally motionless in the air, it's using a PID controller, constantly fighting off tiny gusts of wind. The cruise control in your car keeping your speed perfectly steady even when you go up and down hills? Yep, that's a PID controller. From giant industrial robots to chemical plants to the very plane you might fly in, this simple, super robust algorithm is the unsung hero of modern automation. So the next time you see a machine doing something with this uncanny precision and stability, you'll be in on the secret. You'll know it's probably being guided by this constant, clever little dance between the past, the present, and the future, which kind of makes you wonder, now that you know what to look for, what things in your world do you think are being guided by a PID controller?